Swayam Prabha. Digital India. Educated India.
Hello everyone, today is the second day of this week. In the last class we had seen how to derive weak formulation for a scalar free two-dimensional problem, and we also seen that how to develop a finite element framework based on the weak form. We wrote the element level equations, the general form of element level equations, and then we also discussed how to determine individual term in those in that equation. So what we'll do today is we'll take an example and then implement whatever we have learned so far, implement that to get a solution of a relatively simpler problem, and through that process once again we revisit all the steps involved in finite element method. So to start with, if you recall, this is the two-dimensional problem, general form, strong form of a general two-dimensional problem. And then corresponding weak form is this. If you multiply this strong form by the weight function and take the integration over the domain, it will give you the weak form. And in this weak form, this is the boundary value, the domain defined. This equation is defined over this domain omega, and this is subjected to some boundary condition. There are two boundary conditions on the primary variable and boundary conditions on the secondary variables. The primary variable boundary condition is this, and this is where the boundary condition on the secondary variable gives. This part will give you this natural boundary condition. Now here n is the outward normal. If you take any small length on the boundary, say ds, this will give you the outward normal, and this is nx and this is ny, and this is the outward normal, and this is how the qn, the boundary flux term is written. Now omega gamma u is the boundary where essential boundary conditions, the primary variables, are prescribed, and gamma q is the boundary where secondary variable is prescribed, and together the union of these two will give you the total boundary. And this condition tells you that the essential boundary conditions and natural boundary condition are not imposed on a common boundary. Okay. Now this is the weak form, and then the next is, once we have the weak form, then the test and trial function need to be approximated, and here we approximate these two by the shape functions defined over each element. And then if you substitute the shape functions in the weak form, we will get element equation like this, where kij will give you the coefficient matrix, uj is the primary variable defined at the nodal point for element number e, and then this will give you the source and flux term, right? And this is how this equation can be written in matrix form. Now these equations need to be satisfied over every element to get a system of n algebraic equation. Here n will be the number of degrees of freedom, and n is the number of node as well, because at every node you have 1 degrees of freedom. So if you recall, we can have a special case is by substituting these are 0 and a1, a2, 2 as k, and this special k is this, and it gives you the very well known Poisson's equation. And in this Poisson's equation, the expression can be written like this, where b is equal to this and c is equal to this. Now this we have not derived explicitly, but if you substitute phi and do some manipulation, we can get this expression. Now when n is the number of node, now for instance, if you have a triangular element, and then in this triangular element, this B matrix will take a form like this. It will be a 2 by 3 matrix, and that there are 3 degrees of freedom, and these will be the corresponding boundary flux and source term. Similarly, for a 4-noded quadrilateral, if we take, then this matrix will be 2 by 4 and then 4 degrees of freedom, and these are the corresponding source and flux term. Now, if you recall, so these Poisson's equation can represent varieties of physical process, and in some of the list in the last class given that these are the some of the physical process, some of the phenomena that can be described through Poisson's equation. What we will do today is we will take this example, a 2-dimensional heat transfer problem, and here the primary variable U is T, so this will be essentially U, and that K is the conductivity, and then source variable is F, and then the natural boundary condition is the conduction boundary condition defined like this. We'll take this problem today. So this is the problem. Now, the domain is taken relatively simpler because we have to do all the calculation manually. When we have a program to deal with this problem, then we can take complicated domain, and then we can also increase the number of elements to see the results. So these are the information about the domain and the other constants and the conditions specified at the boundary given. On these boundaries, say boundary number A and B, their primary variable is prescribed, and on boundary BC and boundary CD, the secondary variable, the boundary flux term, is prescribed. F is given as this and the conductivity is this. This is the equation now we have to solve. So we will follow all these steps in finite element method. The first steps, if you recall, the discretization. We have the domain. This domain needs to be represented by a collection of elements. Let's do that. So let us take 2 triangular elements. There are 2 reasons why we are taking triangular element. One reason is we have not yet studied the isoparametric formulation. So once we study know the isoparametric formulation, then we can use we can get the solution of this problem with quadrilateral element as well. But we had already discussed the shape functions of triangular element, and in order to have the shape function, we do not have to, for this triangle, we do not have to really know the isoparametric formulation. So whatever knowledge we have, based on that, we can get the solution. This is one thing, and the second thing is we want to have our computation relatively easier in the sense which is doable manually. So let us take 2 elements, element number 1 and element number 2, and the blue color, these 1, 2, 3T, these are the global node number. Okay. Now, so this is the discretization. Now, once the discretization is done, the next step is to write the element equation. Now, so if we take element number 1, the global node number is 1, 2 and 3, and local node number, say for element number 1, is 1, 2 and 3. These red red color numbers indicate the element number in the node number in element level. Okay. Similarly, for element number 2, 2, 4, the blue color indicates the global node number, and the element level node number are 1, 2 and 3. This is important because when we write element equation, that is with respect to element level numbering, node numbering, but when we assemble them, that assembling needs to be done based on the global node number, right? So this is how we have used this order of numbering, anti-clockwise direction, 1, 2 and 3 here. It is also 1, 2 and 3. So now with this, let us write the element equation for element number 1 and element number 2. Now, as I said, these are the element level node number, and this is global level node number. This is element level node number, and this is global level node number. So before we write the element equation, I would like to take you to the discussion we had in the last week on shape functions. This is the shape functions for a triangle, three-noded triangle we had already derived. We started with an approximation like this, and then this approximation is satisfied at every node, and then we get an expression like this, and then this eventually will give us shape function. These are three shape function, and then this is how the Jacobian can be written for this triangular element, and the determinant of Jacobian will give you the area. This is how the area and the Jacobian, determinant of Jacobian are related to each other. So we know this. So for a triangular element, based on their coordinates in with respect to xy system, xy coordinate system, we can have their shape functions. Okay. Now, so we need to write this. We need to write this equation for both the elements. When we say we need to write this equation, we need to get an expression for Ke, and then expression for Fe and expression for Qv. All these terms now we need to determine. And Ke can be written as this, we have already seen, where B is this and C is this, where K is constant. So C is written as this. Okay, so what we will do is we will substitute this phi 1, phi 2, phi 3 in this expression, and then we can get an expression for B, and this will give you the expression for B. And this is a very interesting expression in a sense. Okay, you see, this entire thing is B is constant. These are all of the nodal coordinates, right, which are constant. So we see that here B matrix is not a function of x and y. For a given element, for a given given nodal points, this will be a constant for that element. And this is not a surprise, because if you recall, when we discussed this element, we had seen that this element is called constant strain triangle because the derivatives of the shape functions are constant over the element, right? That's why it is B is constant, because it essentially involves the derivatives of the shape function. Now, so once we have this, now B is constant. This needs to be integrated over the domain to get the stiffness matrix. Now B is constant and C is constant for this problem, and then therefore the entire thing will be constant. We can take the entire thing out, and then this will be integration of this, and this integration is essentially gives you the area of the element, right? Now if we substitute this, then this will be this will be the coefficient matrix. So for triangular element, what will happen to quadrilateral element, we don't know. We will see that, but at least for this element, for triangular element, we can see that in order to get this coefficient matrix, we really do not have to do any integration. For a given element, coefficient matrix can be obtained like this, okay, just based on the coordinates of the three nodes. Okay, so if we do so, once we know this expression for B, so we can write this is the expression for B1. We know the coordinates of 1, 2, 3. Please note this expression is written with respect to element coordinate 1, 2, and 3. The node number, the element level. So Jacobian will be this, and therefore area will be this, half of the determinant of the Jacobian, and finally K1 will be this, and the coefficient matrix for element number 1 is this. Now this is with respect to blue is with respect to global node number, and if we write the node number at the element level, this will be 1, this will be 2, this will be 3, and this is 1, 2, and 3. Red color shows the node number in the element level, and the blue shows the node number in the global level. Now, so similar exercise we can do for element number 2. So element number 2, B1 will be this corresponding Jacobian and the area, and finally if we substitute, we'll get K2 will be this. This will be K2. K2 will be this. Now this shows the global node number. If we write the local node number, this will be local node number in this is element level node number. This will be 1, 2, 3, and this will be 1, 2, 3. So when we assemble these coefficient matrix now need to be assembled. When we assemble them, we need to assemble based on this global numbering. Now, so we have the coefficient matrix. So one part of this element equation we have, then other two parts are source term and the boundary flux term. Let us calculate the source term. Source term is given by this, and this needs to be integrated again over the domain. So f is constant, our case in this problem. So we can take f out, and then this is the integration of the shape function. Now, these shape functions so we have to perform this integration of the shape function over the entire element. Now this is the shape functions for a triangular element. We have not done this, but you can do yourself and check that if you integrate this shape function over the element, this will give you this result, where A is the area of this triangular element. So once we have this, we can substitute this in this expression, and if we substitute this, we have source term is equal to this, and this is so for element number 1, this will be this. So this is for global node number 1, 2, 3, and for element number 2, the same exercise we can do. It will give global node number 2, 4, 3. So this is the source term now we have. Now next is the boundary flux term. Boundary flux term is, we had a discussion in detail on how to compute this boundary flux term. This is essentially a boundary integral we need to perform, right? Now there we discussed, if you have this integral needs to be performed or evaluated on boundary of an element which coincide with the boundary of the domain where the natural boundary conditions are prescribed. Now all the internal elements where the sides do not coincide with that natural boundary, there is unnecessary to evaluate this, okay, because when two elements join each other, the contribution from both the element will cancel each other. So for element number 1, we don't have to do, because element number 1, there is none of the boundary for sides of the element number 1 coincide with the natural boundary. Now natural boundary in this problem is this one and this one, right? So Q1 gives you this, and then but how to calculate for this? If you recall, now our element numbering is 1, 2, 3. If you recall, we have to this is our element, and then we have to this is 1, 2 and 3. We have to take a local coordinate system S, and on this coordinate system your shape functions will be this will be our shape function. Essentially this integration needs to be done on this line, right? On this line. So this shape function will be 1 minus S by H23, where 23 H23 is the length of this line, length of this side, and this shape function will be S by H23, and this will be H23 is length of the line, and then Q is constant over the entire line. And we had seen, if you have a constant over the entire line, it gets distributed equally on both the node. So this will be the 50% will go to node number 3 and 50% will go to node number 2. Node number 3 and 2 are the element level node number. Now so Q2 will be this, where in this case the element level node number is, this is element level node number 2 and 3. So node number 2, 15 will be node number 2 and 15 at node number 3. Length of 2, 3 is 2. So this is we had discussed in the last class how to do this. We had also discussed, instead of a constant Q, if you have a linearly varying Q, then how to get this how to do this integration, and how we can get this vector. Okay, so once we have all these equations at the element level, next is to assemble them. Now when we say assembling, as we know, assembling means assembling of the coefficient matrix, assembling of the source term, assembling of the flux term, all. So, and this assembling needs to be done based on the global node number. So we have, this is K1 and this is K2. Now this is the assembled matrix. we follow the same approach what we already followed in case of truss, in case of frame, in case of beam, in case of bar problem. Assembling will be exactly same. Now, for instance, suppose in 1 term, here in the global stiffness, global coefficient matrix, so 1 is here, this is 1 and there is no 1 in K2, so 1 is 7.437, this one. Similarly, you take 1 2 is this is 1 but there is no 1 here, so 1 will be minus 875.8750. 1 3 is here, there is no 1 3 in K2, so 1 3 will be as it is. Now, then 1 4, there is no 1 4 in this in K1, there is no 1 4 in K2, so this will be 0. Similarly, if we take the second row, say 2, so 2 1 is 0.8750, there is no 2 1 in K2, this 2 2 will be here, it is 1.75, 2 2 here it is 14, so 14 plus 1.75, it will give you 15.75. Then 2 3 here is minus 0.8750 and here 2 3 is 0, so this will be this. And finally 2 4, there is no 2 4 here, 2 4 will be minus 14 and this is minus 14. Similarly, let's take the last column, the last row, 4. So 4 we have here 4 1, there is no 4 1, it will be 0. 4 2 will be minus 14 and then 4 3 will be minus 8750 and 4 4 will be this 14.8 and 14.8750. Okay, now you can try whether what is the determinant of this this matrix, whether the matrix is singular or not, and then with you remember our discussion in one of the previous weeks when on the properties of these matrices, and if they are singular, what is the physical interpretation of these matrices. Okay, so now this is the global coefficient matrix. Now we have, next is to have the global other two source and flux term, boundary flux term. The source term will be this, so this is F1 we know, F2 we know, and then if we assemble them, so 1 will be 3, 2 here 1.5, 2 here 3, 1.5 plus 3 4.5, then 3 here 1.5, 3 here 3, it will be 4.5, and 4 is 1.5, 4 is 1.5. So, and then finally Q, so we have Q1 and Q2 are this, and then if we this will be 1 is 0, and then 2 is 0 and 0 0, 3 is 0 and minus 15, and 4 is minus 15. So now we have all these terms with us. We have the coefficient matrix, then the source term and the boundary flux term, and then these are the global numberings. Then we write this entire, then step 3. So then we have final this entire equation. It is the equation of the entire system, right? Now in this equation, so this is for global node number 1, this is global number 2, it is global node number 3, it is global number 4, and this is 1, 2, 3 and 4. Now this is interesting, R1, R2, R3, R. You see, when you satisfy, when you write this equation, you will see that that there will be some residue term in first 3, right? We will just shortly see where the essential boundary conditions are specified, and other than that, at these 3 nodes there will be some residues. So R1, R2, R3 are those residues. Okay, so then step 4 is the imposition of the boundary conditions. Now what imposition of the boundary conditions means? In this case, the imposition on the conditions of primary variable. The primary variable is t here, right? Now what conditions we have? T is 0 on this line and t is 0 on this line. So therefore at this t1 will be 0, at this t2 will be 0, and here also t3 will be 0. T4 we don't know. So here t1 will be 0, t2 will be 0, and all these are 0. Right? So if we substitute that, our equations will be like this. So once we have then step 5 is the solution. Now if you remember, once we have this global equation and then boundary conditions are also imposed, then in this equation some of the term of some of the values of the primary variable known and some of the values of the secondary variable are known. Okay, for instance here, and some of the values of primary variable are unknown and some of the values of the secondary variable are unknown. Here in this T4 is unknown here, in this R1, R2, R3 are unknown here. So we essentially have 4 unknowns and 4 constants, 4 equations. So then based on what information we know and what information we do not know, we need to partition the entire equations, and then it will give us the condensed equation. And then this condensed equation we need to solve to get the unknown unknown variable. So if you do this exercise, this will be our condensed. This is how we can get the condensed equations. Only one unknown is T4, and this, the last equation, will give us T4. And if we substitute here, for instance, if we substitute T4, this T4 will be this. This is T4, right? So this is the solution we have. Now once we know T4, we know all these, the primary variable T1, T2, T3 and T4 at all the nodes. We know how these variables are approximated over each element. Then we can calculate the flash term and then do the postprocessing, plot the results and all. Now the thing is, this is not the end of this problem. We will revisit this problem once again in lecture number 40, but in that case we will use different element. Here it is done with 2 triangular elements. We will see what happens to the solution when we use a quadrilateral element. But to use quadrilateral element, we need to know the concept of isoparametric formulation. So first, next class we'll see what is isoparametric formulation, and once that is understood, we'll use this concept, isoparametric formulation concept, to get the solution of the same problem using quadrilateral element. But then again, in the last lecture of this week, we will again revisit this problem. Here we have just taken 2 elements. Even when we see in isoparametric with quadrilateral element, when we try to get the solution, there also we will be probably using 1 or 2 elements. But then we need to see what happens to the solution if we keep on increasing the number of elements. What happens to the solution if we keep on increasing the order of approximation within the element. So what is H convergence and what is P convergence, that we need to see. And for that we need to have a small program through which we can handle this larger problem. That will be discussed in the last class of this week. So we will revisit this problem once again. With this, let us stop here today. See you in the next class. Thank you.